So now let's write this as a theorem. So let n, the derivative of m with respect to y, the derivative of n with respect to y, all be continuous in a rectangular region. We're not going to dwell on this component here. What this basically boils down to is that there's got to be some values of t and y surrounding a point for which these functions are all continuous. We're not going to get into that here, but that is an important piece of the conjecture. Then m of ty plus n of ty times y prime equals 0 is called an exact ODE if and only if the derivative of m with respect to y is equal to the derivative of n with respect to t. And this right here should be a t. Now this condition has to be true because remember, that's the one thing that we built this whole foundation off of, is the fact that those partial derivatives were equal. And therefore that allowed us to think, well, these must be mixed partial derivatives, and they must both be coming from the same derivatives of the same function. So that's where this condition is important, that these two partials be equal. If they're not, then this method will not work. So this implies that psi exists and can be found using integration. So we've already established how that is true. Let's go ahead and take a look at another example to kind of iron this out a little bit more. So in this first case, we have that y cosine t plus 2t e to the y, that's going to be my n of ty. And this coefficient, I see that that's in front of y prime, so that looks like I can identify that as m of ty. And now I have the exact differential equation, no pun intended. We're going to show that it's an exact ODE, and then we're going to solve it using the previous technique. So what do I have to do? Well, if this is already the derivative of some function with respect to, no, I have these backwards. This should be m right here, and this guy should be n. Okay, so this function we're claiming is already the derivative of some function with respect to t. Now we just need to check its derivative with respect to y. So dm dy will equal, so the derivative of y cosine t is a constant, the derivative of y is 1. 1 times cosine t is cosine t. Again, 2t is constant here. The derivative of e to the y is e to the y, so this becomes 2t e to the y. And now we need to check dn dt, and the derivative of that with respect to t, well, the derivative of sine of t is cosine t. The derivative of t squared e to the y is a constant, factor that out. The derivative of t squared is 2t. 2t times e to the y is 2t e to the y. And these are equal. So psi exists. And that's a good sign, because if it exists, that means it is solvable by using this method. So we could say that the ODE is exact. So now we need to go through our process again. So if m was already, now we know that m is already the derivative of some function psi with respect to t, and that function is y cosine of t plus 2t e to the y, then the integral of that with respect to t will give me psi. The integral of this with respect to t will give me psi as well. And so in this integral, I see that I could factor out the y, because that's a constant, and the integral of cosine t is sine t. So this becomes y sine of t. The integral of this with respect to t, well, e to the y is a constant. The integral of 2t is t squared. So I get plus t squared e to the y. And then because when we take the derivative of this, we take the derivative with respect to t, therefore any function that involved y must have gone to 0. So again, this could be a constant, this could be something involving both y and constants, but it would have gone away when I take the derivative of it with respect to t. Now, n, we now know is the derivative of psi with respect to y. So if I integrate it, I probably should be a little bit careful here about my notation. This would be the integral of that. And with respect to t will be the integral of n, which is sine t plus t squared e to the y. And the integral of that, minus 1. Got the minus 1 there. Minus 1. And this is all with respect to y. Well, that's going to equal the integral of sine of t. Well, that's a constant. So the integral of that would be sine of t times y. Just the same reason that the integral of like 5 dx would be 5x. So here sine of t is acting like the 5. And next I see that the integral of t squared e to the y with respect to y, t squared is a constant, so I'll still have the plus t squared there. The integral of e to the y with respect to y is still just e to the y, fun function. Integral of negative 1 with respect to y will be negative y. And then because this is the integral with respect to y, any function that was here with respect to t may have gone away. When you take the derivative of this, the derivative of g of t with respect to y will be 0. So that's an important piece because that acts as a placeholder in the event that we need to come back and reconcile the size. So we know that the candidate size are y sine of t plus t squared e to the y plus h of y. And then the second candidate, that's our first candidate, the second candidate, notice that that also has a y sine of t in it, and they have to be the same side, they're the same function. So notice that that t squared e to the y is there as well. There's a minus y, and then there's a plus g of t. So already here I can see that h of y will match up with negative y, but there's no standalone function of t in equation 1, therefore I can say that this is 0. And again, I can circle these and say those match. Those match. I can put a plus sign here and say those match. And those match right there, which leads me to the conclusion that psi of t comma y is equal to y sine t plus t squared e to the y. And from our solution, we know that as long as all of this stuff worked out, as long as you could find a psi, as long as it's exact, the solution to this ODE is psi of t comma y equals constant. And so that means y sine of t plus t squared e to the y equals constant. Now this is an implicit solution. You cannot solve this for y because first of all there's a y term by itself, so you can solve for this y, but then you're going to have e to the y on the other side. So there's no way to get this y down without taking natural logs, but then that ties up this y inside of a natural log. So that's about where we have to stop with that solution. That's our final answer, right there.